Welcome back. So today what we're going to do is make this heterostructure between graphene and methyl ammonium lead iodide, also known as MAPbI. So yeah, I'm going to show you guys how to make this one today. So here's the end product where we're going to be. Okay. So and this is the 110 plane here. Okay. So let's go ahead and I'll show you guys how to do this. So I'm going to exit out of here. And what we're going to start with is methyl ammonium lead iodide. This is the tetragonal phase. So this is very difficult to make a slab model out of because of these organic groups, as well as because of the fact that VESTA, for some reason, doesn't render this additional atom here. Okay, so anyways, the first thing we're going to have to do is cut this 110 plane. So this is actually relatively straightforward. MAPbI here is tetragonal. This is the 110 surface. So I'm going to apply this transformation matrix to make this surface now the 002 surface. Okay, so this transformation matrix, if you apply the 110 plane, you can imagine now here I have a vector, 110. Now I take the dot product with each column, I get a new vector, 002. Okay, so there we go. So here is now the 002 plane. So if I go to edit lattice planes, you can see this is the 002 plane. So let's save this file, export data. This will be MAPbI 001. We'll save it as a VASP. So what I need to do now, let me press Command W. I'm on a Mac. If you're on a window, you'd press Control W to exit out. I'm going to load up that slab, or this, this is not 001. I have to change this. This is, I'm going to be, let me rename this. 110. Sorry about that. Okay. So I load up the MAPbI that has the 110 along the C-axis. And now what I need to do is make the slab model. So here, because VESTA, for some reason on this system, doesn't render the additional atom here, I need to go ahead and manually do it. So I'm going to go to Boundary, and I'm just going to do this for all dimensions. Select Apply. One thing I will have to do actually is go to Bonds, and I have to delete the bonds in the system. It just makes it much easier to work with. Okay, so I'm going to cut everything around the crystal, but I have to leave the iodine atoms that are around the crystal. Okay. Oh, computer's lagging a little bit. My mouse isn't sticking for some reason, but that's okay. All right, delete these hydrogen. Okay, so that's A. Let's take a look at B. Okay, we have to delete around, but I'm going to keep these iodide atoms, okay? You have to excuse me for this video. My mouse isn't clicking properly. Oh, come on. Okay. So, okay, now we have a proper looking crystal here. And what we have to remember is that in my C direction is where we want the vacuum, right? So we're actually going to keep all of the atoms in the C direction besides these corner ones here, like this, okay? Now this is where it becomes difficult because we're going to save this file as an XYZ. And when you save as an XYZ in VESTA, it saves all the atoms on the screen. Let's go ahead and center on A. And so we have to delete this periodicity in B. This is trivial, so we can just delete this here. If my mouse would ever click. Okay, but now we have to delete the periodicity in A. And we're going to keep these here. Okay, so delete the periodicity in A. And then these pesky ones on the outside here. Okay, so this is pretty bizarre, but trust me, this is what we need to keep here. Well, I mean, there's a chance I could be wrong, but basically you want to maintain this proper sort of termination in the dimension where you have the vacuum. Okay, and this is what a lot of codes that make slabs are struggling with. They would have just cut it here, okay? But you need this extra termination to maintain the charge neutrality. So let's go ahead and save this. So we're going to save it two ways. First way is we're going to save it as a slab, and this will be saved as a vasp. Here we do, we're going to do Cartesian coordinates. And then we're going to save as an XYZ. So slab XYZ. Okay, let's go into PyCharm. You can go into any text editor you want. So here you can see I have 108 atoms, okay? This is actually good. We have charge neutrality here, and I'll show you in a second. So I'm going to copy the atoms from the XYZ into here. Oh, come on. Okay, so now we have to count the atoms. So we have 8 carbon, that stays the same. We're going to have 8 nitrogen, and we're going to have 48 hydrogen, because it's CnH6 for methylammonium. Then we have how many lead atoms? So 73 to 84. 84 minus 73 is 11 plus 1. So we have 12 lead. Okay. And then how many iodine do we have? 85 to 116. That's 31. Plus 1 is 32. Okay. Now let's check charge neutrality here. Okay, just quickly, I'm going to check it here. So we have this methylammonium, we have 8 of them, so that's plus 8. We have 12 lead. Lead has an oxidation state of plus 2. Oops. Right? So this is plus 24. And then we have 32 iodine. So that's minus 32. You add these together, you get 0. So yeah, this is why if you did not include these extra iodine atoms here, you wouldn't have got the correct, you wouldn't have got 32 iodine, you would have got 28. So these 4 iodine, 1, 2, 3, 4. If you didn't include those, you would have got 28 iodine, and then you would have had a minus 4 charge. Oh, sorry, a plus 4 charge in your system, right? But when you include those iodine, you make your system charge neutral. Okay, so one thing we have to do here is we have to actually delete these atom tags, because how it reads is the first 8 are carbon, the next 8 are nitrogen. So I just do a find and replace. So carbon 2 spaces is only here. See, this carbon has only 1 space. This carbon has 2 spaces. So I can just find and replace these with blank lines. And then rinse and repeat for the other atom types. Okay, now finally iodine. Okay, perfect. So this is our slab. Okay, now one thing I'm going to do is add 20 angstroms of vacuum, and let's load it. So this is our slab. Now, VESTA, for some reason, when it comes to this MAPbI system, does not automatically add the periodic boundary condition. So it sort of is taking the periodic boundary condition into account. So if you want to see what the actual slab looks like at this point, you have to go like this, and then delete anything that's periodic image, like that. And yeah, so this is what the actual slab is looking like, more or less. Okay, and so you can see this sort of 1, 1, 0 surface has this alternating kind of pattern to it. It's easier to see with space filling. Okay. And so now what we have to do is fit graphene to this. Okay, so I'm going to exit out of here. Command W, Command W. So here's where it gets tricky. If I load in graphene, you notice graphene is hexagonal, has a hexagonal lattice. And you'll notice that our MAPbI slab has a a tetragonal. Basically all the angles are 90, right? So what we have to do is orthogonalize the hexagonal lattice. We can do this by coming to edit data, unit cell, and applying this transformation matrix to it. See, now the angles are 90, and here you have the graphene. Okay, so I'm going to save this, file, export data, and it's going to be called Graphene Ortho, and we're going to save it as a VASP. Okay, now one thing to notice here is, let's pull up Graphene Ortho. So here's our slab. Our slab has 12.4 and 12.6 as the unit cell axes. So if I multiply this by 3, I roughly get 12.6, which is really good. If I multiply this by 5, what do I get? 2.46 times 5. 12.3, a little bit more because of the 7 after. So roughly 12.6 as well. So what I need to do to get these lattices to match is I just have to do a slight least common multiple, and that basically just means doing the transformation matrix like this here. Oops, I have to reload. So let me load Graphene VASP again. I'll delete this one, Command W, you do Control W. So I press Command E, you press Control E. That just basically brings you right into edit data, unit cell, transform. So this is going to be 5, this is going to be 3, right? Oops, I'm going to press Command Z. I got the wrong graphene. I need to do Graphene Ortho, not Graphene, so apologize for that. Graphene Ortho, edit data, unit cell, transform. This is 5, this is 3, okay, yes. So now you can see we're really close to the sort of 12.6 lattice constant. So what I'm going to do now is I have to save this file as a VASP. Here it's going to get a little bit cumbersome. So save this as a VASP. We're going to call it 5 by 3 by 1. Fractional coordinates. This is very important here. And then what I'm going to do is I'm going to fit this graphene to the slab. So here's how I do this. I open up the 5 by 3 by 1 VASP. And because these atomic positions are in terms of the lattice, I can change the atomic positions by changing the lattice. And I'm going to change them to be according to the methylammonium slab. So I take this 12.4. Sorry, my mouse keeps double clicking. I took the 12.4 from here, and I'm going to put it here. Then let's take the 12.6 and put that here. Okay? So now let's go ahead and reload this. And you can see it is slightly changed. So now what I have to do is go to bonds, delete, apply, and then I'm going to delete periodicity in A and B. Save this as an XYZ. Okay. Don't save hidden atoms. Oh man, now we're going to come in here and copy these 60 graphene, and we're going to put them, we're going to make a new file. We're going to delete hetero. This is what I had before here, okay, when I started the video. And now we're going to make it again. Hetero.vasp. What I'm going to do actually first is copy in this mappy slab. Come back to here, copy this. So I'm going to take this graphene, I'm actually going to insert it first. Okay, so there's the graphene. Now, you can tell for our mappy slab, the highest position is about 12.69 or 12.71. So let's say it's about 13. Okay, so what I'm going to do is actually I have to shift the graphene to be a couple angstroms above that. So I'm going to find this, and I'm going to replace it with 17.00 angstroms, okay? And then finally, I'm going to replace carbon with a couple spaces with the blank line. And then I have to add 60 to this carbon count. So it's 68 carbon. And I'm going to add some more vacuum. Let's add an additional, let's make it 45 angstroms of vacuum roughly. Well, not a vacuum, of 45 minus 17, okay? Plus I think it's some more. You can change it how you want. So VESTA does this weird thing where it makes the graphene like spit out like this here, but you can rest assured that this is fine. So what I'm going to do here is delete the bonds. Yeah, so when it auto perceives the bonds for carbon there, it somehow does that weird thing. But yeah, this is it. So now if you wanted to go ahead and expand this, we'll do -2, 2, -2, 2, -1, just that. Okay. Let's go ahead and let's actually go ahead. Oh no, this is fine. We can delete these and we can delete these. Yeah, and this is our final product now. So I don't have the bonds drawn for graphene, but if you do space filling, you kind of don't need the bonds anyways. But yeah, this is the final product. So we put graphene onto the 110 surface of MAPbI here. Yeah, if you happen to be an expert in doing this stuff, I mean, and you think that I did something wrong, I don't think I did, but if you happen to see something, please let me know in the comments. I think it looks pretty good to me. But yeah, this is how I did it. So there's two tricks here. You had to orthogonalize the graphene to get it to have all the angles be 90. Then you had to find out how to fit graphene onto MAPbI. The way I fit graphene onto MAPbI was I saved its coordinates in direct coordinates, and then I changed the cell axis a little bit. The cell mismatch isn't too great, isn't too terrible. We can go ahead and compute it. For example, along the B axis, you had this plus, or no, this is what we already did here. This plus this divided by 2. Oh my God. Okay, so this was the B value for graphene originally, right? I can press this again. So this is the B value for graphene originally. Then we're going to add it to the B value of MAPbI. Divide by 2, what do we get? 12.7, right? I'm just going to make some room here. So this is the average. Is that 12 point? Oh no, I've got to copy this. Okay, that's the average. And then let's take the difference equals this minus, that's the difference. Okay, and so if I take this divided by the average, and times 100, so it's roughly 1% lattice mismatch between the two. You know, on the B axis, if you wanted to do the A axis, so this is the B axis lattice mismatch. Let's go ahead and do the A axis lattice mismatch. So this one will be greater. So let's first compute the average. Will it be greater? I actually can't tell. Okay, so there's the average, and then let's compute the difference. We'll just take we just have to find the absolute value of the difference, but you can just take the larger number to start. Okay. So then we'll take this difference and divide it by the average. Then times 100. Oh, it's smaller, so it's only 0.8% lattice mismatch. So this lattice mismatch is about 0.8%, I think, and this one is about 1%. So it's pretty good, actually. But yeah, I mean, if you saw any mistakes I made or liked the video, want to leave a comment, you know, leave it in the comment section. And here's the thumbnail. We'll probably use this side for the thumbnail. All right, take care, everyone. See ya.